Hi everyone. So in this video, we're going to be learning about a method for evaluating integrals called integration by parts. So just to give you kind of an overview of like where this course is going next. So far in the class, we've really only learned one method for dealing with more complicated integrals, right? We've learned substitution. And other than that, recently we've really been focusing on applications of integration. So finding volumes, these work problems, finding the average value of a function, things like that. And so in this chapter, we're going to focus a lot more just on integrals. So for some of you, I think you might actually find these next few sections a little easier because there's going to be a little less kind of conceptual stuff going on, and it's more going to be very detail oriented on just understanding how to apply different methods of integration and being able to figure out which method to use in which situation. That being said, we will kind of keep coming back to these problems like volumes or average value. Now that we have that, now that we'll be learning new methods of integration, that will actually allow us to go back to some kind of volumes problems that we weren't able to do before. Okay, so I want to start just by kind of roughly describing what it is we're going to be doing today, and we're going to start by really jumping into an example. So today, we will learn how to evaluate an integral of a product of functions. So an example would be the integral of x times sine of x. So that's something we don't know how to do just yet, right? So maybe just to show you something that we would know how to do, if I just made one tiny change to this, if I just made this x times sine of x squared, then we would know how to evaluate it, right? Then we could just use substitution. But if I get rid of that squared and just make it x times sine of x, there's really no method we have that we can use, right? We don't, you can't do a substitution. You could, if you tried to substitute out the x or the sine of x, neither of those would really accomplish anything. And so one other thing I want to mention that would not work here, and it's kind of a common mistake that students will make, it would not work to say that the integral of x times sine of x dx, you could not say, oh, okay, well, that's going to be, I'll take the antiderivative of x, and that's x squared over 2, and then I'll just multiply that with the antiderivative of sine of x. So antiderivative of sine of x is negative cosine of x. And so altogether, that would give me x squared times, or I'll say negative x squared times cosine of x over 2. That is not correct. And we could even check that that's not correct, right? How can you check whether your antiderivative is correct or not? You can actually just take the derivative, right? That's something I've mentioned a few times. It's very important to know about antiderivatives is you can always check them. So how can we kind of check this? Well, if we take the derivative of this expression here, well, that would be, we can pull the 1/2 out, right? And then you'd have to use the product rule, right? If you wanted to take the derivative of negative x squared times cosine of x, you'd have to use the product rule. And so it would end up being negative 2x cosine of x times, and then we take the derivative of cosine, which is negative sine. And so that's going to end up being negative sine of x times, and then we leave the first function as it is, and that's negative x squared. And so altogether, this would be 1/2 times negative 2x cosine of x plus x squared times sine of x. And clearly that's not the same function as we started with, right? What were we trying to find the antiderivative of? We were trying to find the antiderivative of x times sine of x. And this whole thing is clearly not the same as what we started with. So it does not work to take an antiderivative of a product by just kind of breaking it down and taking the antiderivative of each piece. And this shouldn't be too surprising because derivatives don't even work that way. Right? Like if you can't take the derivative of a product by just taking the derivatives and multiplying them, so why would antiderivatives work that way, right? Antiderivatives are generally even more complicated than derivatives, so it just doesn't work that way. So instead, we're going to use this formula that is called integration by parts. And so I'm going to write it out, and then we'll see why it is true. So basically, the way that the integration by parts formula works is that if you're taking an integral of a product of two functions, you have to choose which one you want to think of as f of x and which one you want to think of as g prime of x. So you're going to have a product of two functions, and you call one of them f of x and you call one of them g prime of x. And we'll do an example in just a moment. And so once you've decided which one is which, well, let me just use some color here. So we're choosing one to be f of x, one to be g prime of x. Once you've decided which one is which, then the way that you evaluate your integral is that you actually just take f of x, so whichever function you decided was f of x, and you multiply it with not g prime of x, but g of x. So you have to take the antiderivative of the function you've decided to call g prime of x. And then from that, you're going to subtract the integral of the derivative of f of x, so f prime of x, times the antiderivative of g prime of x, so that's g of x. So I know that's a lot of words, but we'll see this in an example in a moment. So notice that when you're using the integration by parts formula, it looks like we were ending up with something more complicated, right? We started with one integral. Now all of a sudden we have all this stuff going on. But the whole point of integration by parts is that, first of all, this is just, there's nothing to take the antiderivative of here, right? This is just like a function. That will be all done. You don't need to worry about that. And basically, if you choose wisely what to call f of x and what to call g prime of x, then you'll end up with an integral here that is going to be an easier integral to compute. So why does this work? Well, let's actually show that this is a true statement. And the way we can do that is by taking the derivative of the right-hand side, right? Because, for example, this is completely like unrelated, but why is it true, for example, that the integral of 2x dx is equal to x squared? Like, how could you check that? Well, if you take the derivative of x squared plus c, you get 2x, right? And so how can we test this formula? We can take the derivative of the right-hand side and see whether we get this, right? If we take the derivative of the right-hand side and we get the inside of the integral, that will tell us that this formula is true. So let's do that. So, how can we show this is true? So we're going to differentiate. So remember, differentiate just means take the derivative of the right side, and we'll see that we get f of x times g prime of x, right? That's what we should get if this is true. So if we take the derivative of, with respect to x, of all of this stuff, so we had f of x times g of x minus the integral of f prime of x times g of x dx. So what do we get for this first part? Well, you would have to use the product rule, right, to take the derivative of this first part. And so we would get f prime of x times g of x plus g prime of x times f of x, right? That's the product rule. And then what would the derivative of this integral be? Well, remember, like, what does it mean to take an indefinite integral of a function? It means it's the antiderivative, right? So this part here is an antiderivative. And so what happens if you take the derivative? Well, you just get the stuff on the inside, right? So this is going to be minus f prime of x g of x. And so what do we have? Well, notice that we have two parts that say f prime of x times g of x, and so those cancel out. And so we're left with g prime of x times f of x, and that's exactly what we were trying to take the antiderivative of to begin with, right? So we basically showed that this worked. We took the derivative of our answer and we saw that we got the same thing that was originally inside the integrand, and so, or inside the integral, and so we're good. Okay, so let's actually do an example, because I think this will make a lot more sense once you see how it's actually used. So let's actually evaluate that same integral we started with. So we're going to find the antiderivative of x times sine of x. So we have a choice here. We have to figure out which function we want to call f of x and which function we want to call g prime of x. So I'm going to make the right choice the first time just so we can see how this goes, but then I'll go back and I'll show you what would happen if we had chosen the other way, and we'll talk a little bit about how you can decide which one to pick. So we're going to let f of x, let me just be consistent with my color here. Yeah, so we're going to let f of x be x, and we're going to let g prime of x be sine of x. So let's write this out. So we're letting f of x equals x, and g prime of x is equal to sine of x. So the next step is, when if you look at what the formula involves, we also need to have an f prime of x, and we also need to have a g of x, right? So what is f prime of x? Well, if f of x is just x, then f prime of x is 1. And if g prime of x is sine of x, well then to find g of x, we're just doing the antiderivative. So what's the antiderivative of sine of x? It's negative cosine of x. And you don't need to put the plus c. Basically, it's kind of like when you do a definite integral. Just choose the antiderivative that doesn't have that, where c is 0. Okay, so what is this going to give us? Well, according to our integration by parts formula, we need to multiply together f of x and g of x. So that's going to be x times negative cosine of x. And then from that, we're supposed to subtract the integral of f prime of x, so that was 1, times, and then g of x, and g of x was negative cosine of x. Okay, so let's see what this boils down to. So this simplifies to negative x times cosine of x minus the integral of negative cosine of x dx. So notice that we started with a product, right? We started with the integral of x times sine of x. Now, the only integral we have to evaluate is just negative cosine of x. And that's one that we actually do know how to do just using antiderivatives. Let me make this even simpler by pulling out the negative sign, just because at least for me, my brain works a little better when I have something positive in the integrand. So what is the antiderivative of cosine of x? Well, it's just sine of x plus c. Now we put the plus c. So you kind of save the plus c for the end, basically. So the antiderivative of cosine of x is sine of x plus c. So let's actually check that this worked. So how would you check that this works? You would take the derivative of your answer, right, and verify that you got your original integrand. So if we're trying to take the derivative of negative x times cosine of x, plus sine of x. That's going to be, so we have to use the product rule for the first part. So the product rule for the first part is going to give us -1 times cosine of x. And then we take the derivative of cosine, so that's negative sine of x times negative x. And then the second part of the product rule is just, or sorry, of this derivative, we don't have to use the product rule, we just take the derivative of sine. So that's cosine of x. And so if we simplify this, we end up with negative cosine of x plus x times sine of x plus cosine of x. And notice that we have a negative cosine of x, we have a positive cosine of x. They cancel out, and we're just left with x times sine of x. And that's exactly what we started with, right? So that's good. We just showed that this worked. So basically, you know, what just happened here is exactly what we just showed up here, right? That like because of how you set up the integration by parts formula, when you actually take the derivative, some stuff will cancel out and you'll be left with exactly what you were trying to find the antiderivative of. So one other thing I just want to show you is, you know, what would have happened if we had picked the other way, right? So we picked to let x be our f of x and g prime of x to be sine of x. So let's see what would happen if we tried to do this the other way. So if we take so what would happen if we picked f of x and g prime of x differently? Okay, so we were trying to find the integral of x times sine of x dx. So let's say that now this time, let's say that we picked our f of x to be sine of x. So we're saying now that this is f of x. And then we picked our x to be our g prime of x. Okay, so what would happen in that case? Well, we would then have to take the derivative of sine of x, and that would give us cosine of x. And then we would have to take the antiderivative of g prime of x. So the antiderivative of x would be, I think I flipped my colors here from what I wanted, but that's okay. The antiderivative would be x squared over 2. So why is this a problem? Well, let's see what happens when we actually try to put these pieces together. So we would first do f of x times g of x. So that would be sine of x times x squared over 2. So that part's fine. But then when we do the second part, we want to be multiplying together f prime of x with g of x. So that would now be cosine of x times x squared over 2. So why is this not useful? Well, notice that when we did it the other way, the integral we ended up with here was one that we could actually evaluate. It was simpler than the one we started with. Whereas here, in this example, the integral that we ended up with, this is actually more complicated than the original integral. And so if you end up with, so just like so many things in this class, you know, I think trial and error is really important for getting a sense of what works. If you do try an integration by parts and you end up with an integral that's more complicated than the one you started with, that's a hint that, okay, maybe I should have picked the opposite way. So in general, you know, what's some sort of good guidance for how you pick which is what? So in general, how can you choose what is f of x and what is g prime of x? Well, a couple of things. One thing to keep in mind is that you're going to need to take the antiderivative of whatever you choose to be g prime of x. So you will need to take the antiderivative of g prime of x. So in our case here, that didn't actually really limit us. So if we look back at what our functions were, either way, we could take the antiderivative, right? So the kind of correct way of doing it, we had to take the antiderivative of sine of x, and that was fine. And then the incorrect way, we had to take the antiderivative of x. And in both cases, it worked. But you might see some examples where there's one of the functions that you actually just don't even know the antiderivative of. And so if that's the situation, then you definitely can't pick that as g prime of x. So in some situations, that might kind of push you in one direction. The other fact to keep in mind is that when you get this kind of second integral, what's going to show up in that integral is going to involve the derivative of f of x. Right? And so why, one thing that you can keep in mind is that generally you don't want to choose something, or let me think of how to say this. It's best to choose something as your f of x that has a derivative that is simpler than the original function. Right? So here we started with f of x is equal to sine of x, and the derivative of sine of x is cosine of x, which is like basically a very similar function. And so what ended up happening was that making that change to having a cosine inside of the integral did not give us a simpler integral. Whereas if we look back to, sorry, I have to step back a little bit here. Whereas if we look at this example, we picked f of x to be x. And so the derivative was 1, which is way simpler than x. And so then when we went to do our second integral, that gave us something that was a lot simpler. So in general, if one of your functions becomes a lot simpler, or even just a little bit simpler after taking the derivative, that's usually a good choice for f of x. Because you're taking the derivative of f of x, it's ideal to choose something that becomes simpler. So it is best to choose f of x to be a function that becomes simpler after differentiating. So something like x, right? X becomes sorry, I'm spelling this wrong. Differentiating. X becomes way simpler when you take its derivative. So there will be some exceptions, and we'll mostly focus on those in the next video of functions that are just kind of a little weird, or like these rules don't exactly apply, but in most cases, this is kind of the logic you're going to follow, is make sure that whatever you're picking for your g prime of x, making sure that that is a function whose antiderivative you can actually take, and then also keeping in mind that you want to simplify things. So if you can choose something that becomes simpler when you take its derivative, that's a good choice for f of x. So there's one more thing I want to do before we get into just a handful of examples. So I want to mention there's another notation that is very commonly used for integration by parts. So I want to write down, first of all, the notation that we started with here. So integration by parts. So the notation that we just used, I mean, basically the fact that we called it f of x and g prime of x. So we said that the integral of f of x times g prime of x dx is equal to f of x times g of x minus the integral of f prime of x times g of x dx. And sorry, actually, I meant to do this in my colors, so let me do that because I think it will help with the next step. So we have our f of x, we have our g prime of x, and then we have f of x, g of x, minus the integral of f prime of x times g of x. So the other notation that is much more commonly used actually, but I like to start with this notation just because I think it's a little clearer. It's what you're kind of more used to. The other notation that is frequently used is we'll call the function f of x, the function whose derivative you're taking, we'll call that u. And then we'll call not just g prime of x, but this whole thing here, we'll call that dv. So let me write that out kind of separately. So this would be the integral of u times dv is equal to, so now we would say u times v minus the integral of v, sorry, trying to remember my colors here, that's v du. And so the reason I'm giving this to you is basically, I think personally, I have a lot of an easier time remembering this. And this is just generally the way that if you were to just type in integration by parts into Google, there's a good chance that this is what you would see. So basically, it's exactly the same idea. It's just that you are calling, again, you're calling the function you're taking the derivative of, you're calling that u. And then you're calling g prime of x dx all as one piece, you're calling that dv. So let's actually just see what our example would look like with this new notation. So we were taking the integral of x times sine of x. So basically we would now be setting the x equal to u, so this would be u. And then we would be setting this whole thing equal to dv. So we would say u is equal to x, and then dv is equal to sine of x dx. And so just to kind of show you, like, why does this, so why is this equivalent to what we did before? Well, if you were to divide both sides of this by dx, you would get dv dx is equal to sine of x. So that would, it's basically the same as calling it g prime of x, right? We're saying the derivative of something is sine of x. And so that's why we're going to find the antiderivative of it. Okay, so then we would say from here, we would say, okay, that means that du is equal to 1 dx, right? Because that's the same thing as saying du dx is equal to 1. So it's the same thing as we did above, it's just now calling it something different. And then when we take the antiderivative, we now just call that v. So v would be equal to negative cosine of x. And so when you put this all together, you would get the exact same integral we had before. So you would say u times v, so that would be x times negative cosine of x. And then you would have minus the integral of, so v was negative cosine of x, and then du was 1 times dx. So it's exactly the same integral that we ended up with earlier. So from here on out, I'm going to actually be using this notation. Hopefully it wasn't too confusing that I started with the other one, but I just think it's a little bit more kind of confusing with like how you have this dv and this dx. So I just wanted to show it to you with the other notation first. Okay, so let's do some more examples. All right, so let's say we wanted to evaluate the integral of x times e to the x dx. So let's keep in mind those kind of facts that we wrote down earlier about, you know, what do we want to choose for what. So one of these things we have to take the derivative of, the other one we have to take the antiderivative of. And so just like the other one, notice that if we take the derivative of x, it becomes more simple. And so that makes it a really good choice for our u. So we're going to let u equal x, and we're going to let dv equal e to the x dx. So I should do this, right? It's this whole thing. And so that means that du is equal to 1 dx, because du dx, the derivative of u with respect to x, is equal to 1. And then what about dv? Well, when we take the antiderivative, we get v is equal to e to the x. And so now we want to put this into the integration by parts formula. So it's u times v, so that's x times e to the x, minus the integral of v du. So that's going to be e to the x times 1 times dx. And so this is x e to the x just minus the integral of e to the x. And so we know how to find the antiderivative of e to the x, right? It's just e to the x. And so we're left with x e to the x minus e to the x plus c. And we can check this, right? We can make sure that this is correct. So how would we check this? We would just take the derivative of x e to the x minus e to the x plus c. So what would we get? Well, we'd use the product rule in the first part, and the product rule would give us 1 times e to the x plus x times e to the x. And then we have minus e to the x. And so these two cancel out, and we're left with x e to the x. So hopefully you're kind of getting a sense of how this works. Okay, so what about if we're doing a definite integral? So for example, let's say that now we wanted to find the integral from 0 to 1 of, let's do the same one, x e to the x. So basically it's the exact same idea, it's just that you are now plugging in numbers. So I want to add that back to here where we wrote down our official formula. So for definite integrals, so if you're taking the integral from a to b of, again, we'll say u times dv, that's going to be equal to u times v, so that's u times v. But then you want to evaluate that at b, or at, a and at b, minus the integral, and now this is a definite integral of, again, v du, so v du. So it's really the same thing, it's just that, you know, it's a definite integral, so you have to end up plugging in numbers. So let's go back and do this example. And let's pretend that we didn't already do it, so we don't know what the antiderivative is, just to kind of see how it would go from scratch. So again, we would make the choice, okay, well, it looks like, you know, we want to take the derivative of x to make it simpler, so let's let that equal our u. And then we are going to take the antiderivative of e to the x dx. So that's our dv is equal to e to the x dx. And so the derivative of u is going to be 1 dx. And then the antiderivative will just be e to the x. So what would this look like now? Well, now we would have u times v, so that's x times e to the x. But we're evaluating it now at 1 and at 0. Minus the integral, again, from 0 to 1 of e to the x times 1, dx. So this would be x e to the x evaluated at 1 and at 0 minus the integral from 0 to 1 of e to the x dx. And so you can either evaluate this part right away, or you can take the antiderivative and then kind of do it all at once. It doesn't really matter. You'll get the same answer either way. But let's say that you wanted to evaluate it right away. So when you plug in the 1, you would get 1 times e to the 1. And then from that, you would subtract 0 times e to the 0. And then for our second part here, we would have e to the x as our antiderivative, and we're evaluating that at 1 and at 0. So we would get, for this first part, we just have e. And then for this second part, we would have minus e to the 1 minus e to the 0. So just be careful with parentheses. So one thing I just want to make clear is that we're subtracting this whole integral. So when you go and apply FTC2 and actually plug in your numbers, make sure you put parentheses here, right? Like I just did, so that you're subtracting the entirety of what you're getting by evaluating that integral. And so this is going to give us e minus e plus 1. And so our final answer comes out to be 1. Okay, so I want to do a couple more examples, just sort of to see some of the different ways that this shows up. So let's do an example now of the integral of ln of x over x to the 5th. So at first glance, this might not seem like a product, but it is, right? We can rewrite this as the integral of ln of x times 1 over x to the 5th. And let's actually even rewrite this, instead of writing it as 1 over x to the 5th, let's write it as x to the negative 5. Okay, so now we want to think about what we're choosing to be our u and what we're choosing to be our dv. So one thing I want to point out here is that, let's say we tried to choose ln of x to be our dv. So if you tried to say, okay, dv is equal to ln of x dx. So what's the problem? Well, we actually haven't yet learned the antiderivative for ln of x, and that's something we'll actually talk about in the next video. But you'd be stuck here, right? Because this is not one of the antiderivatives that we know. So this is an example of one where you really are kind of limited in what you can choose, because you can't take the antiderivative of both parts of your integrand. And so you're really kind of forced to set dv equal to x to the negative 5th dx. But this is a good choice for another reason, because if we let u equal to ln of x, well, ln of x actually gets a lot more simple when you take its derivative, right? What's the derivative of ln of x? It's 1 over x. So we get du is equal to 1 over x dx. And then what's the antiderivative of x to the negative 5? Well, we add 1 to the exponent. So that would give us x to the negative 4. And then we have to multiply by the reciprocal. So we have negative 1/4, or let me write it this way. I'll write it as x to the negative 4th over, I'll put it, sorry, negative sign in front, x to the negative 4th over 4. Okay, so let's see what we get when we put these pieces together. So now we have u times v. So we have ln of x times negative x to the negative 4 over 4. And then from that, we're going to subtract the integral of v times du. So that's negative x to the negative 4 over 4 times du, which was 1 over x dx. So this is going to work out well because we started with ln of x, but by taking the derivative, we turned it into something that we can actually now simplify, right? We can, because these are all just x to a power, we can actually put them together. And so we end up with the first part. I'm just going to kind of reorder this a little bit. I'll write it as negative x to the negative 4 times ln of x over 4. And then here, this is going to be plus the integral. I'm just pulling out that negative sign. So what happens when we combine these? Well, basically x to the negative 4, and then here we have x to the negative 1, right? Another way of writing this would be x to the negative 1. And so when you multiply to x to a power together, you add the exponent. So this is going to end up being x to the negative 5. And let's actually pull that 1/4 outside of the integral as well. Might as well do that to make things a little bit easier. So we're now left with x to the negative 5th dx. Okay, so let's now evaluate that antiderivative. And I'm going to rewrite this to put the x back in the denominator. So this is negative ln of x over 4x to the fourth. And then here we have 1/4. And so what's the antiderivative of x to the negative 5? Well, that's the one we actually did to start with, right? We already know that that was this. So it's negative x to the negative 4 over 4. So we have negative x to the negative 4 over 4. And then we'll have a plus c at the end. So now we can just simplify this a little bit. So again, we have negative ln of x over 4x to the 4. And then here, this is the same thing as minus 1 over 16x to the 4 plus c. And then we could even make a common denominator here, right? If we multiply this first one by 4 over 4, we would get negative 4 ln of x minus 1 all over 16x to the fourth. So that's another kind of classic one just to be aware of. If you have ln of x times x to a power, you're generally going to want to choose ln of x to be your u. Okay, couple more examples. So now let's say that we are trying to find the integral of x squared times e to the x. So this is pretty similar to one that we already did, right? We did x times e to the x. And so we're going to make the same choices because, again, think about which of these two becomes more simple when you take its derivative. That would be x squared. So we want to let our u equal to x squared, and we want to let dv equal e to the x dx. And so du is going to be equal to 2x dx, and then v is going to equal e to the x. Okay, so now we put these together. So we have x squared times e to the x minus the integral of, now we want u, or v du. So that's e to the x times 2x dx. Okay, so now looking at what we have here, we don't know how to evaluate this integral, right? Or this isn't an easy antiderivative. However, we can just do integration by parts again. So let me rewrite this so that we can use our color coding again without it getting too confusing. I'm going to pull that 2 outside of the integral. So we have 2 times e to the x, or I'll rewrite it as x times e to the x. So now we just apply integration by parts again. And so this time we're letting u equal to x and dv equal e to the x dx. And so the derivative of x is going to be 1 dx. And then the antiderivative is going to be just e to the x. And so the only thing you have to be really careful about here is negative signs and parentheses. So this is the place where I see most students mess up on this, is they kind of forget to put parentheses. So again, when we're subtracting this entire thing, so we need to make sure we put parentheses around the next thing that comes from the integration by parts, right? So this is going to be expanded into something else. So we're going to have 2 times, and now we repeat the process. So we have u times v, so that's x times e to the x, minus the integral of, again, v du. So that's e to the x times 1 dx. So this whole thing here came from our integral above, right? So that's why we had to put parentheses around it. Okay, so now when we simplify this, we have x squared e to the x minus 2 times x e to the x minus, and so what is the antiderivative of e to the x? It's just e to the x plus c. I guess we should put somewhere. I'll just put it here. And so putting this all together, we have x squared e to the x minus 2x e to the x minus 2 e to the x plus c. And it kind of looks like we should be able to combine things, but actually nothing here can really combine. You could factor out an e to the x if you wanted to, but other than that, there's not really much we can do to simplify. So yeah, so basically, even if this had been like x cubed or x to the fourth or x to the fifth, any power of x, as you keep doing the process, you would make it more and more simple. So, I'm not going to give you an example where you have to do integration by parts like 5 times, but, you might have some examples where you have to do it 2 or even 3 times. So just be aware that like, even if you don't immediately have an integral that is already answerable, as long as you're getting an integral that is simpler, that is getting you kind of one step closer, then you're making progress. All right, last example for the video. So this is going to be a volumes problem, and I want to just show you how we can actually use integration by parts. It will really open the door for what kind of volumes we can find. So we want to find the volume of the solid obtained by revolving the region bounded by. Sorry, I've been trying to write these out ahead of time, but I forgot this time. So what functions do we have here? So this is y is equal to ln of x. So that would, if it were to continue, it would look like this, right? That's what ln of x looks like, but I just kind of took a snippet of it here. We also have y is equal to 0, and then we have x is equal to e. So e is this number here. And we're revolving it about the y-axis. Okay, so what would this shape look like? Well, it would basically be, from the side, it would look symmetric with what we have here. So I'll do my best to sketch this. So something like this. And so in this case, this is going to be a good shell method problem. You could actually do this with washers, but you would have to convert ln of x into being e to the y instead. And I want to do shells because I think it's a good example in this case. So what would the shell method look like here? Well, if we have a sample shell, we can draw it kind of symmetrically like this. So here's what a sample cylindrical shell would look like. So we have our radius. So the radius in this case is just going to be equal to x because we revolved around the y-axis. So really the radius is the same as whatever x value we're on. And we want to include all of the possible x values. The bounds will take care of the fact that this starts at 1. And then what is the height going to be? Well, the height is just equal to the function, which is ln of x. And what are the bounds? Well, the lower bound here would be 1, and then the upper bound would be e. So we end up with the volume being pi times the integral from, I'll write out the general formula first in case you forget. So we want the radius times the height dx. And so in this case, that would be pi times the integral from 1 to e of x times ln of x dx. So this is going to be an integration by parts problem. So how do we know that? Well, it's a product of two functions. And again, you always want to, when you have a product of two functions, think about substitution. But if there's no substitution, that's when you know, okay, this is integration by parts. So let me rewrite this without the colors so we can apply some new colors for our integration by parts. So basically, in this case, so this is one where you might think that you want to make x equal to your u because the derivative of x becomes a lot simpler, right? But we already saw in a previous example that ln of x, we don't know the antiderivative. So we're kind of forced to make ln of x our u. So we're going to set ln of x equal to u. So u is equal to ln of x. And then our dv is going to be x dx. And so our du is 1 over x dx, and our v is equal to x squared over 2, which I know looks more complicated, but basically we'll see that it just kind of works well with the 1 over x. Things will kind of simplify. So our answer here is going to be pi, so we can't forget about the pi, times the, so we do u times v, so that's ln of x times x squared over 2. And we're going to have to eventually evaluate that at e and at 1, minus the integral from 1 to e of v du. So that's going to be x squared over 2 times 1 over x dx. And so things simplify nicely, right, with the integral. So we're going to end up with pi times ln of x. I'll rewrite this as x squared times ln of x over 2, and we're going to have to eventually evaluate that at e and at 1, minus the integral from 1 to e of, so what happens here? Well, the x's simplify, and let's actually pull out the 1/2 here. And so we have the integral from 1 to e of just x, right? Because we have x squared over x. So now we're ready to start plugging some stuff in. So here we get, for the first part, we have e squared times ln of e over 2 minus 1 squared times ln of 1 over 2 minus 1/2 times, so in this case, the antiderivative is x squared over 2, and we're going to be evaluating that at e and at 1. Do I have enough parentheses? No, I need one more. Okay, so what is this? This is pi times, so ln of e is 1, right? Because it's what power you have to raise e to get e. So we just get e squared over 2. And then ln of 1 is 0. And so this whole term is going to go away because ln of 1 is 0. And then we have 1/2 times, so x squared over 2, we first plug in e, then we plug in 1. So almost done here. So now we have pi times e squared over 2 minus e squared over 4 plus 1/4. And that's it. I mean, we could, if you want to make a common denominator, maybe we might as well do that since they're pretty close. So we can make a common denominator of 4. And so we would have 2e squared minus e squared plus 1 over 4. And that's the same thing as just e squared plus 1 over 4. So basically, the shell method works really, really well with integration by parts because you always end up, when you're doing the shell method, you always end up with a product, right, of x times some function, or maybe x minus 1 times some function, or something like that. And so now that we know integration by parts, that will allow us to do a lot more of these integrals of solids using the shell method. All right, so that is it for this video. In the next video, we'll do a couple of more slightly kind of interesting or different kind of examples. And yeah, I'll see you next time.